All right, it's my pleasure to introduce Kris Iyer, who's our Camp Colloquium speaker today. He's a new professor at Cornell in the Operations Research Department. Kris did his PhD at Stanford under Ramesh Johari, postdoc at UPenn, I think under Michael Kearns.
Yes.
And his research covers a range of topics, including some very interesting work on approximate equilibria of dynamic games using mean field methods, which is what he'll be telling us about today.
Thank you, Bobby. First of all, thanks everyone for giving me this opportunity to talk about my research. And so today I'll be talking about mean field equilibria of dynamic auctions, and this is the work I did for my thesis with my PhD advisor Ramesh Johari and Mukund Sundarajan, who is a researcher at Google. So before I jump into the talk, let me just give a brief sort of overview of my research interests. And just to characterize, my research interest sort of looks at the interplay between information and dynamics in market setting. So let me go ahead and explain what it means in terms of like examples of work that I have done. One is so the problem of information aggregation. So this is, suppose you have a finite number of traders who have some private information about, say, security value in the future, and they are trading sequentially with a market maker, and you want to ask under what conditions on the market mechanism does the sequence of trade that they carry out reveals the private information of that they carry. Right? And this could be in the general setting where they are completely rational and they are risk averse, and they can play with they can trade with the market maker repeatedly over time, right? So they might not reveal their information straight away, for example, through the trades. And here I find sufficient conditions on the market mechanism. In particular, I show that if the bid and the ask in the market converges over time, then the trades will reveal the private information of the traders. And so this is the case where like all the traders have private information, so there is information asymmetry. And the next work, which is currently ongoing, is so I want to study like how do traders choose between different price levels that differ in what kind of execution guarantee that they get. So let me give an example. So even in a simple stock exchange, you can go ahead and put in a market order where like you agree to buy or sell at whatever price it's determined by the market. So your trade happens with certainty, but usually you lose out on the price. Or you can put in a limit order that says, okay, I want to buy or sell at this price, but there is a chance that my order will not get filled. So in particular, I might have to wait for some time, or the price will just move very far away and I would have to cancel my order. So there is some execution uncertainty, and you want to ask if traders are sort of informed about the price movement. They have some private information. How do they make this trade-off between the two options? And in particular, how does the presence of a uncertain option affect the welfare of the whole market? So anyway, coming back to this talk, so today I'll be talking about dynamic auctions, in particular learning in dynamic auctions. And the motivation for this talk is mainly the sponsor search market. So let me give a brief overview of the market. So yeah, so many of you, if you haven't installed an ad block software, would see this pretty often. So if you search for something on Google, along with the organic results, you'll see some sponsored results on the top and the side. Right? And so here, for example, there's just one organic result and everything else is sponsored results. And the way these sponsored ads effectively sort of form a huge chunk of revenue for Google. And the way these ads are allocated is through an auction mechanism. So advertisers come to the market and they bid on different keywords, and the winners get their ads placed. So more precisely, so if you can go ahead and start a campaign on this website on say Google AdWords, where before the campaign you decide on a set of keywords that you want to bid on. So, for example, this was something I ran quite some time ago, and I had chosen keywords like auction, operational research, and so on, right? And my name, for example. And in particular, if anybody comes and searches one of these keywords, they would I would be chosen to participate in an auction along with all the other advertisers that bid on the same keywords, and the highest bidder gets their ads placed. And I won't go into the details of the auction mechanism right now, but the main idea is that as your bid increases, the likelihood of getting your ads placed increases. And so to go into a bit more detail, I want to say that the good that is being auctioned off is not an impression but an ad click. So in particular in these markets, so what you bid is known as a cost per click. So you bid an amount, and you only pay if a user comes in and searches for that keyword and then ends up clicking on your particular ad. So even if your ad is shown and nobody clicks on it, you won't pay. So the good that is being auctioned off is an ad click. So this is the most common form of auction where you bid a cost per click and the highest bidder gets the ad placed. But if you think about it, what advertisers care about is a conversion. And what is a conversion? Conversion can mean different things here. So this is how an ad click converts into revenue, either current revenue or future revenue. And for example, in the most common sense, what you care about is whether a user who searched for your keyword clicked on your website and then came to your website and bought whatever it is that you're selling. But in more general setting, it could be that they came to your website and watched some video and you got some brand exposure, or they signed up for some newsletter which could convert into some future sales, and so on. So conversion can mean different things, but the thing is that there is some mismatch between what is being sold and what you actually care about. Right? And what this means is that so advertisers, as they participate in different auctions, they sort of maintain estimates about what is the likelihood that a click is getting converted into revenue, and they update these estimates as they go along. So in particular, these auctions have dynamic incentives. So the sequence of auction that any particular advertiser participates as is dynamic. These are coupled heavily, right? So what I do now will affect what I do in the future. So in particular, advertisers have many other dynamic incentives. In particular, they face budget constraints. So most big companies have maybe quarterly targets and quarterly budget, and there is an interesting dynamic because the marketing wants to use up all the budget within the quarter. So there is they want to match it exactly. But it could be also as I said, they might have some targeted exposure target. They want to show the ads to these many people over some time, so they have some demand constraints. And so in general, advertisers face many different dynamic incentives, and this has practical impact. In particular, you want to ask, from the advertiser's perspective, how should they go ahead and bid in the sequence of auction that they participate in? Right? So in particular, if I have dynamic incentives, I don't know how to go out and participate. In general, I'll have to solve some complex problem that would depend on many other things in the market, like how the future market evolves and so on. And from the perspective of a search provider, this is again an issue because they want to know what their future revenues are, for example. So they want to know how the bids will evolve over time. And in particular, they might want to care about how changing the parameters of the model, and in particular, they want to see how the market design influences the revenue they get, for example. So the point I want to make in this talk is that if you go and analyze this problem using usual game theory techniques, so this is a very difficult problem, and it becomes really challenging. And even if you are, in particular, it becomes very intractable, and even if you are able to find an equilibrium, it's very hard to say that that is an equilibrium that matches how advertisers actually behave in practice. So the point I want to make is that using answering such questions would require us to have novel methodologies and novel modeling techniques. And so this would require sort of making some approximations and looking at how advertisers behave. So just to give a summary of the talk, so first I'll be focusing on the learning aspect. So the advertisers are learning their conversion rate over time. So I'll present a model of repeated auctions where bidders are learning the item. And I'll use a large market approximation known as a mean field equilibria to go ahead and analyze this. And I'll show what, for the next 45 minutes that using this approximation allows us to obtain a very simple characterization of bidder behavior. In particular, you can show that the bidder's bid will optimally balance between the exploration and exploitation aspect that they would see. And finally, depending on the time, I'll use this characterization to ask questions about market design. In particular, how does the format of the auction that is being repeated affect the advertisers, the search provider's revenue, and how can a search provider go ahead and set reserve prices in this auction optimally. So let me go ahead and present a market model. So the market model that I'll present has a lot of components. In particular, I have to specify what it is that the bidders are learning, what is the auction that is being repeated, how are bidders coming in and going in the market, and how do they value a stream of rewards that they get. So I'll go ahead and explain all of them one by one, and I'll make assumptions as I go ahead, and I'll try to explain how these assumptions relate to practice. So I assume that we have a market where we are selling a sequence of goods through a second price auction, and these goods are identical across the auction. So we are selling multiple identical copies of a single good. Just to give an example, for those who may not know, a second price auction is an auction where the highest bidder wins and pays the second highest bid. And the nice property of this auction is that for a static case, truthful bidding is dominating, in the sense that irrespective of how others play, it is optimal for me to just give my value, bid my value. So right now I'll be focusing on second price auction, but later on I'll talk about what happens if the auction format is changed. So I assume that in each auction, alpha agents are randomly sampled from the population, uniformly and independently. So there are many assumptions to this statement, so let me go ahead and sort of unpack it. So first of all, we assume that in each auction, the participation is restricted to a particular, a small subset of the agents, right? And this is natural because, so even in practice, not all advertisers participate in each and every auction. So in particular, they might, for example, they have some interest about keywords, and they only participate in the auction, the keywords that they are interested in. And even otherwise, they might have some budget constraints which prevent them from participating in each and every auction. And you can assume this sort of restriction to a subset as an exogenous way to modeling these other constraints that they may have. And we assume that the size of this subset is fixed, and each auction alpha agents are chosen. And this is just for making analysis simpler. You can actually assume that this is some random quantity. As long as it's bounded above, it's all fine. But the more troubling assumption is that we are choosing the agents independently across the auction. And this is definitely made for making the analysis simpler. And in practice, you would actually see there is a lot of correlation in which bidders, which advertisers participate in the same auction. But right now, let's just assume that this is the model weakness, and a better analysis would include correlations among the bidders. Right? And we assume that agents, the agent population is dynamic. In particular, agents arrive and leave the market, and this is natural. And the way we model this is that these agents have geometric lifetimes. So they participate for a geometric number of auctions, so randomly distributed. And just to make everything, make the size of the market stable, we assume that each time agent leaves the market, a new one comes in. And the reason we make this assumption is twofold. One is to model the actual arrival and departure in the real market. And the second reason is we want to study learning in these markets. And if we assume that agents persist forever, then in steady state, everybody would know their value because they would have learned it. So the only analysis you can do is sort of a transient analysis. And that's much more difficult. So we wanted to study learning in a steady state system. And so this is a way to sort of ensure that there's always learning going on. So what is it that they are learning? So we assume that each agent has an unknown private valuation V. So this is some number between 0 and 1. And this dictates the distribution of rewards that they get. So in particular, we assume that the reward is either 1 with some probability V or 0 with probability 1 minus V. So what this means is that if the agent has a private valuation V, then this is the likelihood with which a user sort of clicking on that ad will come to the website and convert into revenue now or in the future.
Okay, so the valuation is not in between 0 and 1, but just at 0 or 1.
No, it's between 0 and 1. It's a real number, 0 and 1. But this is unknown to the agents. And so this is the quantity that, yep.
So the assumption of private values means that when other advertisers enter the market, it doesn't affect my rate.
So this is an assumption that
since one of your co-authors is actually at Google, do you happen to know to what extent reality reflects that assumption?
So for certain keywords, definitely reality doesn't is not captured here, and the reason is, for example, the user is the same, right? So there might be some user characteristic. For example, he might be a male in certain area who might be searching for a car, for example, and then you know that the likelihood that this user, once he comes to your website buying, would be very high, and this is like high uniformly across all the participating bidders. So there is some common value aspect, and that is definitely a more challenging problem, and that is something I haven't modeled here.
Yes. Quick related question. So if you try to relax this assumption, would it be possible to talk about the mean field equilibrium at all?
Yes. So you can. So it's much more harder, but you can definitely state what should be a mean field equilibrium with common values. That is something I've been exploring, but maybe I can talk to you about it. So as I mentioned, this is the thing that agents are trying to learn over time, and so I need to specify how is it that agents learn, and we assume that agents are Bayesian. So in particular, they have priors, then they update it as they see observations. So in particular, we assume that agents have some initial beta prior. So this is a distribution characterized by 2 parameters, and this is the mean and the variance for the prior. And the thing to note here is that by varying these parameters, you can model advertisers with various different means and uncertainty about their valuation. Right? And as I mentioned, the belief update is through Bayes rule. So let me explain how this happens. And just for an aside, so we just make this assumption for simplicity. You can actually, in the paper, we actually define a large class of initial priors where you can do the same analysis. So in particular, so belief update can happen in 3 events. So effectively 2 events. But first of all, an agent may participate in an auction and then lose. Right? So in particular, in this case, he does not get any observation about his valuation, and this means that there is no update in the beliefs. So this is the simplest case. Secondly, the participating agent might win and then get a positive reward. So in this case, the agent becomes more optimistic about their value, so they update their beliefs in this manner, where like you put more weights on the higher values, and this can be represented by a beta distribution where the first parameter increases by 1. The next scenario is where the agent wins the auction, but there is no conversion happening there. So in this case, you can represent the posterior by where the second parameter increases by 1. So in particular, if we let Sk denote the belief parameters after the kth auction, then the transitions in the belief undergo this transition diagram, where depending on what event takes place, the belief parameters update. So this is how agents learn in the market, and I need to specify. So I have specified like how they arrive and leave, and how they learn, what is it that they're learning. I need to specify how do they value the stream of rewards that they get. And we assume that agents are risk neutral. So in particular, they just maximize the total expected payoff over their lifetime. And in particular, we assume by the per period payoff is just the reward they get minus the payment they have to make in the auction. So this is just a simple model for how they value the stream of rewards. So now, containing all, if you're specifying all this, what we obtain is a dynamic game among the agents in the market. So you need to specify, analyze how they would behave. But before I do that, let me talk about a simple scenario where what would happen if the private valuation is known to each agent. And if the private valuation is known, then there is no learning going on. And in particular, that means that there is no value for learning, and the auctions completely decouple. So in particular, this is just a repetition of a static second price auction. And since I mentioned in a static second price auction, bidding your value is weakly dominant strategy, we just assume that each player would just bid their value. And so we have a very simplistic description of agent behavior in this market. So now coming back to our model, what if the private valuation is unknown? Well, if the private valuation is unknown, then definitely they have there is some learning going on, so they have some value for learning. In particular, if they win, they would get one more observation about their private value. So they have some value for information, and that would mean that agents would overbid. So they may bid above their current estimates of their value. But if you want to ask how much would they overbid, so this is a very complicated problem, and in particular, it's very hard to determine. And the reason is because each agent's strategy will depend on how other agents in the market are behaving, and in particular, what they believe the future evolution of the bids would be. So it's hard to say how much they would overbid. But our intuition says that they would overbid above their current estimation. And so the standard way to go about analyzing these questions is, as I mentioned, that as a dynamic game, and the equilibrium concept you use is a perfect Bayesian equilibrium. So let me specify what a perfect Bayesian equilibrium is. So first of all, perfect Bayesian equilibrium assumes that all agents are completely rational. Right? So in particular, each agent tracks every other competitor in the market, right, and maintains beliefs and plays optimally against them. So beliefs about the entire future evolution of the market, right, at each point, which are history dependent. And then the second requirement is that each agent, these beliefs that they maintain are consistent, in the sense that after each update they get, they'll update these beliefs over entire future evolution using Bayes' rule.
So that does mean that each agent knows whether another agent gets a reward or not?
So, so we can model it by different ways. If they know it, then it's fine. If they don't know it, they'll have to maintain beliefs over that fact, and they'll have to update that belief. So anything they don't know about, they'll maintain beliefs about it, and they keep on updating as they get more and more information. So these belief structures could be about, like as you mentioned, about like every other agent in the market and so on. So these could be very complex quantities. So in particular, the PB suffers from two issues. So one is as we addressed, one is the intractability. So in particular, due to these large dimensional belief spaces and so on, often showing an equilibrium exists is itself very difficult. And in particular, as a result of this, we also obtain sort of a dual thing, which is like these equilibria are in most practical settings implausible, in the sense that and in practice, if you go and look at advertisers, they don't keep track of each and every competitors that they face, but just have some estimates about the things that they are interested in, and they go ahead and bid it. And sort of the thing is that you also don't obtain any structural insight out of these equilibria, because these equilibria can depend on the strategies in this equilibria can depend on many different things, and it's hard to say how it depends on your beliefs and so on. So the point that I want to make in this talk is to say that so using this notion of a mean field equilibria, a large market approximation, will allow you to overcome these hurdles and to obtain sort of very nice structural insights about how agents behave. And you can also, I'll also show like these equilibria are more plausible in practice. Yes?
I think PB is using a refinement of the mean field equilibria. Is there any relation between the set of mean field equilibria and PB?
So I will show an approximation result. It's not exactly what you mean, but something related. So the main idea of a mean field equilibrium is that so if the market size is really large, then it doesn't make sense for you to track each and every competitor, but sort of assume that the rest of the market is going to be in a stationary state, and now you are just a single person who's playing repeatedly against a stationary market. So this is basically a large market approximation, and there is a long line of literature going back in economics and so on. And this main idea comes from basically statistical physics, where like you analyze a molecule of a gas, assuming that the rest of the gas has nice macro properties. So as I mentioned, in a mean field equilibrium, the agents do not track each and every competitor, but instead assume that the rest of the market is stationary. And one way where these kind of assumptions can arise in practice is, again, in the sponsored set setting. So this is Google. So Google provides usually to the advertisers who run campaigns some bid landscape information. So what is a bid landscape? So this is a weekly data, and for the operations research keyword, my bid was $1. So if anybody clicked on it, then I would have to pay $1. So this is the estimated number of impressions I got and some clicks that I got. But Google sort of runs this counterfactual hypothesis and says, okay, instead of $1, if you bid some other value, what is the number of impressions you would have got in the market? And so this sort of gives you the distribution of bids in the market. So effectively, we can assume that advertisers use this to sort of model the rest of the advertising market. And if you assume that this bid landscape is going to be stationary, then your problem becomes sort of very easy to analyze. So more precisely, so mean field equilibrium has two components. So one, there is an optimality part, which says that from a single agent assumes that the rest of the market is fixed in a steady state distribution, and then just computes the optimal actions. And then we require a consistency part, which requires that if each agent follows this, the optimal action that we found here, then in a large market, the steady state that arises should be the one that they assume to begin with. So in the context of dynamic auction, what this means is that a mean field equilibrium is a bid distribution and a strategy, C, such that each agent assumes that the bid distribution is fixed. And so in each auction that we participate, the bid distribution is G, and then goes ahead and computes a optimal strategy. And then if each agent follows this optimal strategy, then the bid distribution that arises in a large market should be G. Yes?
Are you going to define what you mean by strategy in this context?
So in this context, strategy is basically, given your beliefs, what is the bid you would make?
Okay, so it maps two natural numbers, M and N,
To,
bid.
yes, that's right.
Could you explain more about the differences between this Field equilibrium and Bayesian-Nash equilibrium? Because
So-
if we substitute the bid distribution G for my belief distribution G, then it looks like it is a description of perfect Bayesian equilibrium.
Perfect Bayesian equilibrium or a Bayes-Nash equilibrium?
Sorry, Bayesian-Nash equilibrium.
So a Bayes-Nash equilibrium is a static concept, right? So you're just looking at a single game, and if you assume the bid distribution is this, then you just compute what is the current optimal thing to do. But we are looking at a repeated, like a dynamic game, so this is like infinite horizon, say, and so we are looking at steady states of these infinite horizon markets. Yes.
So just to make sure I understand what the strategy is capable of, the inputs are M and N.
Yeah.
I do not care about how many auctions I have already participated in.
So
That's not an input.
That's M plus N.
Oh, okay.
So it will turn out that, let me go ahead and talk about, so it will turn out that the decision problem that these single agent faces, if you assume like the rest of the market is stationary, is very nice and very nice, has nice properties. So let me talk about it. So let me just characterize, assuming a large market, what should be an optimal strategy for a
Just want to, just, I'm sorry, everybody keeps interrupting. So, is the agent also take into account that his lifetime is finite?
yes,
Yeah, so this is a part of the strategy.
yeah, this is.
Okay.
I mean, they know that they are their lifetime is geometrically distributed, but they don't know how long exactly. They will. So we look at a stationary market where the bid distribution is fixed, right? So in particular, from a single agent's perspective, they participate in a sequence of auction where each competitor's bid is drawn IID according to this distribution, say G, and this is IID across bidders and across time. And we assume that it's a repeated second price auction. So in particular, what this means is that from this bidder's perspective, if the bidder makes a bid B, the probability that they will win in the auction is just the maximum over alpha minus 1 other bidders. And similarly, we can write down, using the fact that it is a second price auction, what their expected payment is given a particular bid B. And so this is a bit more complicated expression, but the thing to note here is that these two quantities are completely determined if you specify what G is. So let's look at the agent's decision problem now. Right? So given their belief is xk, so if they bid some particular value b, their current expected payoff is just the probability with which they win the object times the mean expected reward from getting one copy of the good minus the expected payment they would pay. And so after winning, their beliefs will undergo some transition. So that transition is given by this transition diagram as we looked before. And finally, we know that the agents have geometric lifetimes. And these three things together imply that the agent's decision problem is basically a discounted dynamic programming problem. So in particular, this has nice structure. There is another strategy that is Markovian. You just need to look at current strategy. You don't have to look at the entire past. Right? And there is a strategy that is stationary. You don't have to look at how long you have lived. You just look at your current belief. So only thing that matters is your current belief. So the parameters, current parameters M and N. So already we saw like a drastic reduction in the complexity, and in particular, we can go ahead and actually analyze this problem. And So this is the agent's Bellman equation, and so in particular, given the bit distribution G, we can write down the expression for the value function V. This is just the starting from belief as what is the maximum you can extract from the market, and this has many components. So this is just the expected payoff in the current auction, and all the other terms have this quantity beta, which is just the probability of survival for one more period. So the geometric parameter, and this is just your future expected payoff on winning and getting a positive reward. So a conversion happening. This is you win in the auction, but you get 0 reward, so no conversion happens. And this is just the probability with which you don't win. So we have this complicated Bellman's equation, and the thing to see here is that there are many terms that involve the quantity, the winning probability QBG. So one thing we can do is sort of collect this and try to simplify the expression. And so simplifying, we obtain this expression where we have sort of condensed all the complexity into this quantity CSG. So as it will turn out, this quantity CSG will be important for us, but let's just focus on the agent's decision problem. Okay? So the agent's decision problem is this maximization problem. And the thing to note here is that these quantities QBG and PBG come from a second price auction where the bid distribution is fixed as G. So in particular, what this means is that the agent's decision problem is same as the agent's decision problem in a static second price auction, where the alpha minus 1 competitors' bids are drawn from G, G, and the agent themselves has a known valuation CSG. This is just a static second price auction, and as I mentioned, in a static second price auction, bidding your value is optimal. What this means is that in this case, bidding this quantity CSG is optimal for the bid. So in particular, we saw that, so we have a nice characterization for bidder strategy. So we call this quantity CSG to be the conjoint valuation as S, and the reason why we will do it will become clear in a second. So this is the expression for the conjoint valuation. And if we see, this has two components. The first, that is the mean, given your current parameters, belief parameters, and there is this extra quantity which we call the overbid. And we actually show that this is positive, so it's an overbid. So in particular, if the agent has no value for information, they don't care about future, what they would bid in an auction is just their mean. So this denotes what they would bid if they were completely exploiting their information. So what the remaining thing does is just the value for information, so how they explore about like finding more about their valuation. So this denotes the value for information, and you can actually show that, I mean, it's very easy to see that the overbid is basically expected marginal value of one additional observation. So this is what you would get if you had one more observation, and this is your current future value, and so this is just the expected marginal value of one additional observation. So now if we come back to this slide, we can answer this question: how much would the agents overbid by? And this is just the expected marginal value of one additional observation. And note that this is a very simple description of agent behavior. And we obtained this primarily because we looked at a large market. And that allowed us to sort of remove all the other aspects, like what would other advertiser do and so on. So assuming that the rest of the market is stationary, we can characterize how agents would overbid in this market. So let me just talk about more theoretical results. So in particular, do these equilibria exist? So the first theorem in our paper is that mean field equilibrium does exist in a large market where each bidder just bids a conjoint valuation in a repeated second price auction. Yes.
So for that, you're going to have to put together this
conjoint valuation with some sort of distribution on the m's and n's and aggregate it all and get back your
Yeah.
valuation on G.
So you assume that when they come to the market, they have some initial M and N, and as they play this strategy where they bid their conjoint valuation, that induces some bid distribution in the market, and this should be consistent. Right? So in particular, the proof is basically showing this fixed point theorem, where you start with some bid distribution and compute the optimal strategy, CSG, and then you find what is the bid distribution that is realized, and you want to show that this map has a fixed point. And so the picture is actually slightly more complicated than what I have presented here, but the thing is, like, if you impose the right topologies on the various spaces, you can actually use a shorter fixed point theorem, and that shows that this infinite dimensional map has a fixed point.
So what is the right topology?
So yeah, I mean, it basically boils down to imposing just a C1, I think, where like actually it's just it's a compact interval, so you just impose L2 metric on this thing, and you get. So the main difficulty here was to find what topology works rather than what the topology is. The reason is that if you have to sort of balance, because there are multiple spaces here, you have to sort of balance how strict the topology is, so that because you want to show that this is continuous, but if you put too strong a topology, then the next map won't be continuous and so on. Yeah, so
does the proof give uniqueness of the fixed points?
no, so it's just an existence. Yeah, I mean, yeah, I'll talk about it. So, but before that, so mean field equilibrium exists, so we make this large market assumption. So the question is, does this actually imply anything in a small market? So is it a good approximation to the case where there are a finite number of agents? And so the complication with having a finite number of agents is that you would meet the same advertiser, say, repeatedly. So in that case, it would make sense for you to keep track of what happened in the past, so that you can probably try to influence the other person's bid and so on. So in particular, the hope we have for approximation in this case is only in the asymptotic region. So we have this theorem where we say that like the mean field equilibrium becomes better approximation as the number of agents in the market increases. And the way we do this is we assume that in a finite market, all the other agents are using the mean field strategy, right? And we allow just one agent to probably deviate to a optimal history-dependent strategy. And we show that as the market size increases, the maximum that they would get sort of converges to zero. Yes?
Is that equivalent to proving that if you had a finite number of players and all of them were playing internationally, whatever it happens to be, as the total number of players goes to infinity, you're going to converge to a zero?
That's not exactly the same argument.
Would it be equivalent to this? Or is it something?
No, I think what you said is would be a stronger statement than what I'm saying, and I think that sort of relates to what you mentioned about like PBE converging. So in particular for every finite market, if you allow everybody is fully rational, they might follow some perfect Bayesian equilibrium, and we don't show that this perfect Bayesian equilibrium converges to the mean field equilibrium. We just show that if everybody else is following mean field strategy, and then, but you can say that if you allow, so such a strategy, you can say it's like an epsilon perfect Bayesian equilibrium in a finite market, right? Because no single agent can get more than epsilon by deviating. So the set of epsilon perfect Bayesian equilibrium converges to the mean field equilibrium. So the way we show this is basically we use, so we look at the market as an interacting particle system. So each agent is a particle, and whenever they participate in auction, they interact. And we look at some quantity known as an interaction set of an agent, which is basically all the agents that they have influenced in the past, in their lifetime. And we show that we use a result from statistics known as propagation of chaos, which shows that as the market size increases, any two randomly chosen agents' interaction set are disjoint. So in particular, from an agent's perspective, the competitors they see in any auction would be independent from them because they have never interacted with them, and hence the bid distribution will be close to the optimal, the one that they assume in a large market, and hence the strategies would be close. So what this means is that mean field equilibrium is also a good approximation to agents in a finite large market. And just want to say that due to behavioral reasons, it could be a good approximation even in like small finite markets, like where there are few agents. And for example, in a sponsor search setting, as soon as advertisers don't keep track of others but just look at the bid landscape, you can say that this approximation can kick in. Right? But that's not a rigorous statement. So I have 10 more. So let me just conclude with the applications to market design. So in particular, the first question you want to ask is like, what would happen to the revenue if you change the auction format? So I assume that you are using a repeated second price auction, but instead you could have other auction formats. For example, first price auction or third price auction and so on. And in particular, so we look at the class of standard auctions. So these are all auctions where the winner is the highest bidder, and a person bidding 0 pays 0. And this just says that participation is effectively voluntary. They can decide not to participate. So yeah, there are many different examples of standard auction, and the complexity here is that so unlike a second price auction where bidding your value was a dominant action, here like you need to incorporate the strategic behavior of an agent even in a static setting. So for example, in a first price auction, the static setting says you would underbid your value because you don't want to pay your value if you win. And this is in conflict with the overbidding that you would incur if you want to learn. So how do the agents balance between these two quantities, these two incentives? And so that we show something we call a dynamic revenue equivalence theorem, and effectively we show that the maximum revenue over all mean field equilibria of a repeated second price auction market is same as the maximum revenue over all mean field equilibria of any other standard auction market, any specific standard auction market. So in particular, yes?
Is it known whether there's a revenue equivalence theorem for PBE in place of MFE?
So I don't know of a revenue equivalence theorem for PBE. I don't think there is one. But even here, there is some complexity here because we don't show uniqueness here, as I mentioned. So the way we make this statement is that for every mean field equilibria of a repeated second price auction market, there is a mean field equilibria of a repeated standard auction market that attains the same revenue, and vice versa. So it's a bit more a stronger statement than what I actually presented here. So what this says that all standard auctions yield the same revenue to the auctioneer. So in particular, if the auctioneer wants to sort of increase his revenue, he has to go beyond the class of standard auctions. And so one sort of standard way to go beyond the class of standard auction is restricting the supply of goods. So you set a reserve price, and you don't sell if the bids are below the reserve price. And in a static auction, the way if you set a reserve price, there are two effects. First is that you sort of exclude some people whose values are below your reserve from ever winning, so you're sort of giving away revenue from them, whereas you charge higher revenue from those whose values are higher than your reserve. So in a static setting, a market operator sets a reserve price that balances between these two quantities. But in a dynamic setting, there is an additional effect. In particular, setting a reserve would impose a learning cost. So in particular, it will preclude some agents from ever learning about their valuation if they think their valuation is very low. But even for the ones that have high estimates, it reduces the incentives from learning because even if your value is high, you would pay more. So this sort of creates some distortion from the static setting.
I have a question about number 2. So I understand the number 1, but if I know that my valuation is greater than the reserve price, then why would I try to bid more? I don't get why auctioneers can expect more revenue from those bids.
So if there are more than one participants, right? So if you might bid at your reserve price, but then somebody else might just bid you a little bit above you and win, right? So even with reserve price, you would bid more so that you sort of ensure that you win substantial amount of time, substantial fraction of time, but you won't bid as much because you are paying in expectation more than without a reserve. So there is an additional effect in a dynamic setting, and you want to study how should a market operator include this learning cost in setting the optimal reserve price. So just consider again a repeated second price auction setting, and as I mentioned, due to learning cost, the agents will change their behavior, right? So a market like a Google, for example, sets a reserve price, and then given the reserve price, the agents will behave in such a manner that will result in a different mean field equilibrium. And what this sort of states is that this defines a game between the auctioneer and the agents in the market. Right? In particular, the auctioneer sets a reserve price, and then they play so that what results is a mean field equilibrium. And in particular, you can look at this in two different approaches. One can look at a Nash equilibrium setting where the auctioneer sets a reserve price assuming that the bid distribution is fixed, and the agents behave given a reserve price, they behave according to the corresponding mean field equilibrium. And in equilibrium, these two are consistent. So in particular, in this case, the auctioneer does not incorporate the fact that if he changes the reserve price, the bid distribution will change. Whereas you can look at a Stackelberg approach where the auctioneer basically anticipates that changing the reserve price would change the bid distribution. And here he basically, for each reserve price, computes the mean field equilibrium and looks at the revenue and chooses the reserve price that maximizes the revenue. And we compare these two approaches using a numerical computation. So we just use an iterative method to go ahead and compute the mean field equilibrium. And in all cases that I have tried, the bid distributions converge. Yes?
So here, you were working on the assumption that the auctioneer knows the value and all the others have price variation 0. If I'm going to use this in securities market, you would have the auctioneer who wouldn't know the value, and one of the bidders would know the actual value of the auction. The results carry.
So I don't assume that auctioneer knows the value. Auctioneer only knows the distribution of values. So it's different. I mean, but yeah, if the auctioneer knows the values, then he would have to. It will be a different problem. Yes.
It's a little confusing. When you're saying that you're using a numerical computation, you also told us that you don't have the uniqueness results.
Yeah. So that's true, but I don't prove uniqueness theoretically, but in practice, verified and like, I mean, I don't have a great answer to this, but if you run numerical computation like an iterative procedure, starting from different initial values, you converge to the same sort of equilibrium. So there is a reason to believe there might be a uniqueness.
Experimentally, there was uniqueness.
Huh?
Experimentally, there was uniqueness.
Experimentally, there was uniqueness. Yes. At least for the range of parameters and the distributions that I looked at. So yeah, let me just quickly run through. So by definition, adopting the Stackelberg approach is better, so your revenue would be higher. And numerically, we see that the additional payoff that you get over setting a reserve in a Stackelberg approach is higher than what you would get in a Nash approach by 15 to 30%. And this depends on like what your initial choice of parameters are, like what distributions that the beliefs come from, and so on. So in particular, by ignoring learning, at least in this model, under this numerical approach, we see that the auctioneer might incur a substantial loss in revenue. So let me just conclude quickly. So hopefully I convinced you that these kind of markets are very hard to analyze using standard game theoretic techniques, and you need sort of new approaches, new approximate approaches. And the one approach I presented was a mean field equilibrium, and you can use this to analyze other, I talked about learning, but you can use this to analyze other dynamic incentives like budget, and people have already looked at it, budget constraints and demand constraints. And at least in the learning case, you can obtain a very simple characterization of agent behavior. In particular, you can show how they balance between exploration and exploitation through this conjoint valuation. And I also talked about how you can use this as a tool to inform market design. Like how do you choose reserve prices, or how do you choose auction formats, and so on. So let me end this here. Thank you. Yes.
So you argued that it's very hard to compute a PBE. So I'm wondering if you have any qualitative results on how the PBD differs from the field equilibrium. I mean, the approximation result shows that in some sense they are close together. But a question I'm curious about, for example, is compared to the bid distribution you would get in MFA. In PBE, would you expect the bid distribution to stochastically dominate that, or be stochastically dominated by it?
The problem is like if you go ahead and define PBE for this model, you will have to like specify what is the history in the market, and you need to specify what are the observations that each agent makes. And this is a very complex thing, and I don't even know how to say anything other than just writing down what the strategies are and specifying what the equilibrium is. So in other work that I did about information aggregation, I looked at a perfect Bayesian equilibrium. There I could say something there, but here it's, I think, almost hopeless. So I have no idea. Yes?
So on your slides, you had reference to the work by Leon's philosophy. This is one part which I do know.
Yeah.
And all of the transitions, all of the passing to the limit they do from the finite set of players to the mean field limit is done under the assumptions that your personal payoff depends on the state of other players, but not on their actions.
Yes. And in particular, the aggregates, like a sort of a mean state of other players. Yes.
So, sort of the moment you say the state, I'm going to use a feedback strategy, the state of the agent of the player immediately gives you the exact bid that player will be making. All of them will be making the same. You're sort of making it easier to talk about ability. Is there a reason to believe that your strategies reducing the Nash equilibrium would be the game of finite number of players here?
So in a finite game, it need not be. There could be mixed. In general, you'll have to look at mixed Nash equilibrium or whatever the light equilibrium concept is. So the approximation result that we look at, so that allows for any history dependent, or like where you can use randomized actions and so on. So we don't restrict to like just pure strategies or so on. Like everybody has given a state, you have to choose a particular bit. Irrespective of what potential history dependent optimal strategies are, given everybody else is not using them and you're only one person deviates, if the market size is large, the benefit you would get is bounded above. And I mean, I actually characterize in the paper the convergence rate.
But that's under the assumption that the rest of them are following prescribed.
Yes. Yeah, so that is the approximation result I show. In particular, if everybody allows, so there is one way you can analyze this, like you look at. So there are some papers that they look at this, where like some auctions where you look at for finite market, you compute the equilibrium, like a perfect Bayesian equilibrium or whatever, like a rational expectations equilibrium or so on, and you show that these equilibria converge to the equilibria of the infinite market. That's a much more harder problem, and so one paper that I know of, the way it does it, it actually computes the equilibrium of the finite market, and then just proves a limiting theorem. So one question you can ask is, like, if you already have the equilibrium of the finite market, why do you need to care about the infinite approximation? So
Perhaps because it's cheaper to compute.
yeah, so yeah, but definitely for like, but yeah, not I mean, I don't show that in this case. Yes.
Okay, let's thank Kris again.